Good morning, all. Um, Welcome to chapter 10, and this whole chapter, as you will probably figure out, is all about current electricity. So I'm going to ask you to do something if you feel you want to, and that is take a break partway through this. Just maybe a 10-minute break, get up, walk around, maybe go get a drink or something, and then come back. But anyway, let's get started. So last chapter, chapter 9, was all about this bad boy here, static electricity. And we discovered that static electricity is charge at rest. Okay? What I mean by that is that it is a build-up of charge. So charges accumulate on, say, an object. So electrons, an imbalance of electrons building up on an object, for example. Current electricity is different. Current electricity refers to electric charges that flow in a circuit. So electric charges, or electrons, can't spell, try E-L-E-C-T, electric charges flowing in a circuit. And we'll talk about what a circuit is later. And electricity flows along a conductor. We know what a conductor is because we talked about conductors and insulators before. From an energy source like a battery to a device that uses the energy. So, for example, if this is a wire and this is a light bulb, so electrons are going to flow through this, cause the light bulb to glow and flow out. A joule, not the type you wear in a ring, but a joule is a measurement of energy. Okay? And electrical energy is useful because you can take it and you can convert it from one form to another into other forms of energy. And for example, we've already talked about light, so you can translate that into, or convert it into light. You may be thinking of other things right away. For example, a heat. If you've got a baseboard heater or something like that, is a good example. And then when you're listening to your music, it can also be turned into sound. It can be turned into motion as well. Why don't I put that in? Electric motors, for example. And the joule, capital J, and the symbol that we use, I don't like to write out joule all the time, so we use the capital J, and that is the measurement for energy used. A light bulb, so this is an incandescent bulb. This is the type that are actually being phased out now, and this would use about 4,000 joules per minute. Water, though, heating stuff up to boil, for example, requires about 300 kilojoules. So a kilo anything, 1 kilo is equal to 1,000. Okay, so this is basically 300,000 joules. So that's a lot of energy compared to light. Electrical energy in a circuit, as we mentioned before, the charges are actually electrons. And I hate writing electrons out over and over and over again, so a lot of the time you're going to see me do this. E, lowercase e, with a negative superscript saying that it has a negative charge. Okay? And the amount of energy that each individual electron has, that's called its electric potential. Think of it as every electron that's moving along has a certain amount of power to it, a certain amount of ability to do work. So that's what we're talking about, electric potential. And we'll talk about that again more later and when we talk about voltage. Voltage is a measure of electrical potential. Another thing that we're going to talk about is something called the load. So load, this is something that converts, it's the converter into another form. So the load in an electric circuit is any device that converts electrical energy or electricity into another form of energy. And I don't know if we want to, we've already talked about a few examples above. You can think of, if you wanted to think of different appliances or like TV set or whatever, that's fine. Okay? Pathways in circuits. And these pathways are really these guys here. They're the wires that connect the energy source to the load. I've actually drawn one. Here is electrical wire. There's the load, and energy is coming from somewhere. But we're going to be talking about a circuit because the word circuit actually means like a circle, like a completed loop. So we'll talk more about that in a few minutes. And what this does is it creates a control path through which the electrical charge that is the electrons, I'm going to put it here, can flow. Metals are the best conductors. Copper is the most commonly used, but it's not the best one. Copper is cheap, and it is more flexible than aluminum. But aluminum is actually the better conductor of electricity. The problem with aluminum is that in time it gets brittle, so that it can crack and break. And if you do that, your wiring is no good. So copper won't do that. So that's why we use copper. Okay? The diameter of a conducting wire depends on its use. The diameter of a conducting wire depends on its use. For example, in a microchip, the conducting, and microchips don't typically use wires, they just use, not drawn out wires, they just use very, very thin, what would you call it, like flat pieces. And this is just to allow a few, this is only a few atoms wide. Okay, so they're very, very tiny. The wire in a house, and you probably have played with wire yourself already. So these are just maybe a few millimeters. I know I use wires a lot for non-electrical things as well. I use them to bind up my electrical cords because I'm too cheap to go out and buy clamps and stuff like that. Transmission lines, those big overhead wires that you see heading up over mountains and stuff, these can be up to 2 centimeters wide or more. 2 centimeters. So 2 centimeters, you guys probably have a greater idea of that. I'm an old guy, so 2.5 centimeters is about 1 inch-ish. And when you're talking about very large quantities of cable, they can be even bigger than that. I've seen cables that are approximately 3 inches across. So 3 inches across is like super big. And those are used, for example, before we had satellite telephone connectivity. We had to, if you wanted to talk to anybody in Europe, you had to use the transatlantic cable, which is like several inches thick. Huge, huge, huge. Okay, page over. Okay, now this is a time that I'm going to suggest that we've gone for almost 13 minutes. So right now you can pause, stand up, go take a walk around, and come back, and then restart. Okay? Okay, now that you're back, what is this for? Let's look at page 302 of our text and 307, and I think I'm going to lead you through part of this, and then I'm going to release you to do some homework. Okay. Now, you can get this information if you do not even have a hard copy of a textbook. There is a digital copy in today's lesson, so please avail yourself of that, okay? So, difference between primary and secondary electric cells. Okay. First of all, when we're talking about a cell, you've probably talked about this as a battery. That's not actually the right name for it. That is a cell. A primary cell This is something that is disposable because it cannot be recharged. And obviously then a secondary cell is one that can, right? This is just your good old rechargeable batteries. Okay, and so you'll find those in your, those are things that in your laptop, your for you guys, your Chromebook, or your laptop, depending on what you got, and your phone. Anything that you plug in to recharge contains some sort of secondary cell. Okay? Incandescent light bulbs. We're going to LED, but an incandescent bulb basically is like this. It has electricity or electrons. Oh, I should have done a different color. Electrons go into this very, very fine wire, and there is something, it's a coil like this, and you can look at old incandescent bulbs, you actually see the coil, this, and it's joined to another little post, and so the electrons come out this other side. Now, what this is that this is called a filament. It's called a filament. A bit. And the filament gives light when it glows hot. And what that means is that it's basically a heater. Okay, because it heats up. Now, the problem with that is that any heater, heat takes a lot of energy. To be made. Okay. Okay. Now, I believe that an incandescent bulb is only, I think it's 20% efficient. That means that, let's use dollars instead of other units of measurement. Let's say that you spent $1 to turn on a light. Only only 20% of that actually made the light. The other 80% was heat. And if you ever try to grab a light bulb, an incandescent light that's been on for a while, you'll burn yourself. So that is lost heat. It's good for nothing. It's sad. Okay, so symbols are just a way to make drawing easier. easier and understandable to everybody. Because the symbols are universal. In other words, if I showed a symbol of a light bulb to a Japanese person and to a Spanish person, they both understand it to mean the same thing. And so there's only a few that we're going to really talk about or use in this course. I'm going to do 4 right now. The first one is the cell. So we talked about this bad boy here. See how long it's taking. Oh, you can't see that. See how long it takes me to draw a cell, and even then it's questionable. So if we're going to use this in a going to use this in a diagram, we do it this way. Now, just, you should probably highlight this or something. This shorter guy here, this shorter part of this, don't make these the same. You need one that's longer than the other. The shorter one, this is where the electrons come out of. Okay? This is the negative end, because electrons are negative. That means that this is the positive end. Okay? So this is the positive end. This is the negative end. Electrons come out of the negative end. When you wanted to do more than 2 together, so this is where, again, start that. Here's the first cell, and I put another one next to it like that. For example, in a flashlight you see this. So this is called a 2-cell battery. Battery implies 2 or more items. In World War II, when we talked about an anti-aircraft battery, you were not talking about one gun. You're talking about a series of guns that they worked together to shoot at enemy aircraft. So if you're going to do this, you just add another one on. So here's the first cell. So big one, shorter one, big one, shorter one, wire. So again, this is the positive terminal, negative, negative, and electrons are going to flow that way. Okay? So far so good. A switch, so here's a switch. Pretend that I am, here's how do I do this? Here's a switch. Now all a switch is a way of breaking contact. So if this was an electric wire, it's an electric wire, and we do 2 little circles like this to indicate this is a switch. So this is an open switch. This is when the lights are off. So this is lights off. Because the electrons can't go through. They're stopped right here. Can't go through. Lights on is when you have flipped the switch and now the electrons can continue through to the light bulb, and so this is lights on. Okay? Light bulbs, again, here's my drawing of a light bulb with the contact in the bottom. And this is the light bulb. And let's go here. There's the filament. so. So this is a light. You're going to see different versions of this. One is like I drew before. You go up like this, go filament like that, and down like so, and you just put a circle around that. That's one version. There's another version that doesn't even go that far. It just goes one loop. So basically it goes like this, goes a loop, comes out, puts a circle around there. Both these are the same thing. These are both light. The official word is not lights, it's actually lamp. Okay, so so that's official. Okay, now for you, what I want you to do is turn in your text. There are 3 diagrams that ask you to either draw or to label, and so this should take you all of about maybe 4 or 5 minutes. On the back side there are 3 other short questions, and again this should be keep you well under time for today. So today is going to be a little bit of a shorter version. Okay, so we've done about 26 minutes worth of chatting today. There is one video. It's pretty short. It's maybe about a 10-minute video, and then the rest of the time, the 24 minutes, you should have more than enough time to do today's homework. Okay, so once you finish that, shoot me a picture via text, and Bob's your uncle. Love you, go away, and I will see you next day. Bye now.